Hey everyone, this is part 2 of the checksumz pwn challenge from IrisCTF. So in the last video we fully solved the challenge, but it wasn't reliable. I was just guessing the kASLR offset by just taking a pointer and doing a bitmask and on it. Instead we're going to work on the intended solution and actually do some heap spraying and find more reliable pointers that point to some kernel address. The intended solution, so the challenge author was Lambda, they said the intended solution was opening ptmx files so that you could create or spray TTY structs. So we'll take a look at that. We'll show how you can spray those objects and what it looks like to spray them. And then someone else in Discord, Urge, said that they were able to spray pipes. So we'll take a look at how that works. And yeah, that should be it. I'll give the briefest of introductions to the SLUB allocator. But yeah. So as a quick reminder for this challenge, we were exploiting the dev checksum character device driver, and we had a arbitrary relative read. So there was some buffer, and we were able to read anywhere past the buffer. And we're looking for a kASLR leak. So it's just some pointer that points back to a kernel symbol that we can use to calculate the base of the kernel. So then we can do our mod probe attack, or mod probe path attack. Cool. So when we allocate objects on the kernel, that allocation method is called, it's a SLAB allocator. And so to get more information about the SLAB allocator and what's happening, the kernel exposes a file called cat proc slab info, which is pretty cool. And so what this is going to do is it's going to tell us about all these little bins that the kernel is using to allocate objects. So we can see at the top we have active objects, num objects, object size, and objects per slabs, and pages per slab. So I'll recall those out as we go down. The kernel allocator is kind of split into two parts. There's like these named bins, and that is these, and then we have these general purpose bins, which we'll talk about in a second. One thing that's cool about the kernel is it is a very long, cool about the kernel compared to userland applications is the kernel is very long-lived, and it is less general purpose compared to malloc, or the heap implementation within libc. Libc doesn't know what its users are going to do. Like users do crazy things. As someone who runs a software business, users are always doing something crazy. And so like you have to build it. Malloc has to be very general purpose and just can't be too specific. And because of that, you can't optimize things too much. Whereas on the kernel is a long-lived process. I mean, a long-lived execution, I guess. And it has data structures that it knows it's going to use repeatedly. And so it can optimize for those. And so these are the named bins. And so task struct, for example, this is your process struct. While the kernel is running, it is going to create and use many task structs. Right now there are, 55 of them in use. Each task struct is 500 or 5,952 bytes long. And so instead of having to like malloc this and then free it and then malloc out and free it, what the kernel does is it creates a SLAB dedicated just to task structs. When it creates one of these slabs dedicated just to task structs, this particular one is 8 pages long. So if you remember, 8 pages is 4 kilobytes. So 8 times 4, this is 32 kilobytes of memory, a continuous memory dedicated just to task structs. One particular slab is. Each one of these slabs can hold 5 of these task struct structures because each of them is about 6 bytes. So we said it was 32,000 bytes continuous, and it holds about 30,000 bytes of actual task struct data. So that's how you read these. So these are the named ones, and they're for like very common structures that the kernel uses a lot. I think cred, the cred jar was specifically pulled out because it's an attack target. And even though it's, I guess it is still used a lot, so it probably makes sense for it to be in its own slab isolated by itself. Yeah, for the most part, it's just like very commonly used objects that you can kind of skip a lot of the initialization code and just have them ready to go whenever you need them. Then we get into more of the general purpose ones. So this is DMA. I'm not too familiar with these. I'm pretty sure the DMA stands for direct memory access. Again, never really used it. This is the RCLs. I think this means reclaim. Never really used them. You can see there's no objects in these, so I'm sure they're useful at some case, but I'm not too familiar. And then there is the general purpose kmalloc. So these are the structures that would normally, so this challenge was a little bit weird, we'll talk about it in a second, but these are the structures normally created by the kernel that is used by the kernel, and they're just general purpose bins. I mean, this is almost like the fast bin, the fast bins have different sizes in the heap. So this is malloc 64, for example. It's going to allocate 1 page for this particular slab, and it can fit 64 chunks in there into a single page. And we're currently using 1,152 of them apparently. Here is, and then somewhere over here, like all the way over to the right, it's not on the page, but that'll tell us how many pages are currently allocated, but you can just do the math. I mean, if you really were curious, this divided by 64. The bin or the slab that we're interested in is the kmalloc 1k. So our driver, our checksum driver, it's doing two different alloc calls, kernel alloc calls, and they both call into this bin or this slab because they are both greater than 512 bytes, but less than 1k bytes. So they go into this one. Each one of these slabs is 2 pages long, so 8,000 bytes. And if it's 8,000 bytes, that means you can hold 8 of these objects in them because they're all 1,000 bytes. Cool. One thing I said is that this challenge was a little bit weird. Normally, the slab that we would be using for exploitation is the kmalloc CG and then one of these. And the reason for that, and actually let me just show what that looks like. So we can do sudo. This is my host machine, so I'm just going to grep for CG, and we can see we have all these CG bins. And the reason we usually exploit the CG bins is because of this line here. Untrusted allocations triggered from user space should be a subject of the kmem accounting and must have the GFP account bit. Normally we use this GFP kernel account shortcut. And so they go into this separate bin. And really it's just saying like, if the user is touching the structure, it's possible they can exploit it. So let's just put it far away from our other kernel objects so that, if the exploitation happens, it happens over there. So what was strange about this challenge though, is it was actually disabled. Someone else in Discord pointed it out, but config memcg is not set. And so because of that, this structure is not live. And so what it means is that there's just more structures that we can kind of play with. So this would go into the standard normal kernel slab, whereas if then we did this would go into that private one for user objects. Since there's technically this probably should be using GFP kernel account because you can modify this as a user, and same with this one because we're going to be modifying this data structure from user space. And so because of that, technically I think that would be more correct. But like I said, this challenge did not have the CG bins enabled, so that just opens up the number of targets we can use for spraying. So Lambda, the challenge author, said the intended solution was to use an object called ptmx, and you can open it, and when you open it, it creates a TTY struct, which is, again, it's a popular method for doing heap spraying, specifically for the 1K bin. So this is the code for opening it. It should look very similar to the driver code, because again, this is just another character device. And so, this file is located at dev ptm. So let me actually go back in. Start root debug. It exists at ptmx right here. But from my understanding is you can open up with one of these ptmx devices, and it creates one of these like pseudo TTY files, and there's like a master and slave. So it's like a way for two applications to talk over like a virtualized terminal device. What that actually means, I'm not too sure. Like, I guess these terminal devices, my understanding is the benefit of it is just a lot of applications depend on certain input characters and like a certain terminal feel. And so you can create these terminal devices. Like when you SSH into something, you want that like terminal feel. Like, you want your control C's and your up and down arrows to work. I guess another example is like when you get command injection on a web server, you can spawn like they call it like the poor man TTY or whatever with Python. I think that is the terminal feel that you're going for. And this is a way for two applications to communicate over one of those terminals. That's my understanding. But for exploiting, we don't really care. We're just trying to spray a bunch of TTY structs. Cool. So just going through the function, I'm pretty much just going to go down to what's important. We're looking for the call that is allocated that creates one of these structures, and then we want to look inside the structure and see if they have interesting things. If we go all the way down, there's this TTY init dev. We're going to click on that, go to the implementation. We go through here, we can see this TTY struct. So this is the common target. Here's a call to allocate TTY struct. We go to that, and we can see it is going to do a kASLR on the size of TTY, and it's going to put it in the GFP kernel account. So again, this is going to go into that CG bin, or normally it would go into that CG bin, but there is no CG bin on this challenge. So cool. We're curious what the size of the TTY struct is. We can go to the definition. And it looks like a pretty big structure. Again, we want it to go into the kALOC 1K bin. So it needs to be greater than 512 bytes. To check the size, what we can do is go into the debugger. So I'm going to go here. We're going to do gdb x attach.gdb. We're going to continue, we're going to cancel, and we're going to print out the size of struct tty struct. And it is 656 bytes. So we are good. So when it allocates one of these structures, it'll be big enough to go into the 1K bin. So now that we know that the structure is the right size and it's going into the bin we want, next we need to make sure that it has a pointer to somewhere in the kernel, and like a kernel pointer, not a SLAB pointer. So we can look at the structure. Oops, not that, this one. This is the tty struct. We can see it's pretty big, and it has something interesting here. So this ops pointer, so most likely it defines a bunch of function pointers that do different operations. And we can see what this is, what it is. Like you can see these are all function pointers. So let's scroll all the way down. It's a chunky boy. And we can see tty operations is a bunch of different pointers to functions. So most likely these are pointer to kernel functions. And so most likely this will be a kernel leak. Where it's actually set, so we need to figure out, this is the tty object is being created. If we scroll down a little bit, we'll see that this ops thing is being set by driver ops. If you follow all the code around, it's not too exciting, but eventually you'll find out it's being set from this driver, the ptm driver, just from a couple of functions ago, and you can then print out the ptm driver, because it's just a static symbol, ptm driver, and you can find the ops, and so this is the ops object that is being copied over to our new objects. So that means we have an object, it fits into the correct bin, and it has a pointer to the kernel in it. So when we do our spraying, what we're going to do is, we know the SLAB has 8 spots in it. We're going to create the character device, and then we're going to insert a bunch of these tty structs, and then we're just going to look for a pointer that kind of looks like this, so that it ends in 89480, and that will most likely be the ptm Unix 98 ops symbol. And once we get this address, we have our leak, like a known leak. So cool. We can see what this looks like in code, how to create these objects and spray them. This is just a little spray.c, and the way this works is I have a function called dump slab info, and it's going to cat proc slab info and then grep for the kmalloc 1k. And this is just to prove to ourselves that we're actually filling up the intended slab. And then there's a wait for key space. So first thing it's going to do is it's going to dump the slab info, then we're going to wait for a key press, and then after that it's going to open up a bunch of checksum devices. And this is just to show that we are creating objects in the 1k kAlloc bin. And then it'll print it out and it'll wait. Then afterwards, we're going to spray these tty structures. Again, I said how to do this is just by opening up a dev ptmx file. That is all you have to do. You don't even have to save the returning FD. You probably should. You probably should close all the files, but it's a kernel that we're going to kill immediately after, so it doesn't really matter too much. Then we're going to dump the slab info, and if everything works well, that slab should have a lot more entries in it. And then afterwards, I'll show, we're going to cover pipes in a bit. I'm just going to go through the source code again, just kind of get you used to going through the code. But this is the pipes. Again, very simple. We're just going to open up pipes. The way pipes work is kind of similar to that. It's just a two-way data transfer. Another one of those IPC methods, inter-process communication methods. Pipes, you probably see it like if you do, I don't know, cat, lol, and then word count. This structure is a pipe. And so you can just create pipes by calling the pipe syscall. And so this is just an array with 2 elements. So this specific one, I'm creating 100 of these, but each one of them is just 2 integers together, and you'll get the file descriptor of each side of the pipe as a response to this pipe syscall. And then the kernel has to create an object to remember the pipe, and so that is where you get that 1K object. And then it dumps the slab info after that, so we can see what the objects look like. And then one last time, it'll open a checksum, so if we want to do some debugging, we can. So let's run this. Let me exit this. Let's go to exploit. Let's make spray. Let's go back. Python. Let's start another one. Python cd exploit. Python m hp server. And then we'll go to this guy. We'll cancel and restart just in case. We'll do gdb x attach.gdb. And then we will we'll hit continue here, and now we're going to launch that exploit. Stuff all over the place. And by exploit, I just mean spray. Cool. So it downloaded, and the first thing happened. So the first thing that happened was we created Oh, we haven't done anything yet. So by default, we have 344 objects in this 1K slab, or of the 1K slab size. Now, after opening up 100 checksum devices, we remember each time we open up a device, it creates one entry for the checksum device and one entry for that default name field or whatever, and each were size 1000. So it should go up by 200, and we can see it went up by 200. So perfect. Next, we're spraying all those TTY structs. Each one of those, for some reason, I think I only did 100, but I guess there's 2 allocations in there. I don't know what the other one is, that create the TTY structs. And now we have 744. So we can at least see that as we spray this object, it is filling up the correct bin, which is exciting. And then pipes, which we'll talk about in a second, we can see it goes up by another 100, which is what we'll expect, which we'll talk about. And then it's about to create the last checksum device. At this point, let's open up the debugger. We're going to cancel. We're going to break on checksumz open. We're going to hit continue. We're going to hit continue. And the breakpoint should exit. Cool. The reason we exit or set a breakpoint in checksumz open is vmmap and the search function, which I'm about to use, they only explore memory they've seen. And so I just want to have it make sure it's seen these memory mappings before, because the kernel space is absolutely huge. You can't scan through all of it. So we need registers with addresses that we're interested in scanning through. Like I said, the object that we're looking at was it ptmx driver? PTM driver. Cool. So like I said, there's the PTM driver object, so we can print it out, and it has this ops field to make sure that our spray is working. We can search for this pointer, and there should be a bunch of them if the object was sprayed correctly, and we can see, yes, they are all over the place, which is great. So all over in our slab, there's this pointer, and so we're just looking for one of these that ends in a 89840, and once we find that leak, we can calculate to the base of the kernel very simply. Cool. The other object so that's pretty much it. Looking at the actual solve, let me go back to child.c. So this was our exploit.c. This is our solution code. So the only addition I had to make to the file was here. So I already had that code that was looking for interesting pointers. Now, every time we leak a pointer that looks like a kernel pointer, we're going to see if it ends in 89360. And so this is that operation structure. That if it says we found it, we found a PTY Unix 98 ops, that was the symbol name. And then from there, we can calculate to the kernel base because they're at known offsets from each other. And then from there, we can calculate to modprobe path. So nice and simple. The other structure that someone in Discord mentioned, I think it was Urge mentioned, that they used pipe buffers. And so this is how you allocate, or this is the code in the kernel to create a pipe buffer. It's alloc pipe info. We can see there's an alloc call here, so maybe this is it. But if we take this line and we print, we can see this is only 168 bytes. So this is probably not the structure for doing the pipe. Instead, if we keep looking, there's more stuff here. Eventually, it's going to do kASLR over here with size up pipe buffer. Pipe buffer sounds like the object we want. So we print out the size. And strange, it's only 40 bytes. But if we look a little bit closer, it's doing kASLR on the number of objects we want. And so we want to know how many this is. If you scroll up, pipe buffs is defined here, pipe def buffers. It is 16. So it is allocating 16 of these pipe buffers all at once. And these pipe buffers are actually structures that hold the buffers used by the pipes themselves. So here's all the little pages. So you have just an array of objects that hold pages that contain the data that you would pipe to. So cool. This is another structure that we could use. And to show what that looks like, and I guess we also need to show that there are pointers on this object. And so going back, we can see there's this pipe buff operations. And you can, if you follow through the code, you'll figure out where the operations is set. Eventually, you'll find out it is on this pipe FIFO FOPS structure, this one right here. And so this is the symbol we're looking for. And you just look through the code. Eventually, you figure out where it gets assigned to the operations. So cool, we can print that out. We can print it out. It was pipe FIFO FOPS. And there it is. So cool. And we can examine it, get its address. Oops. We can get its address. It exists here. So this is the pointer we're going to be looking at. And we already leaked them as part of that spray code. So we can just search pointer, make sure they exist. And there should be a whole bunch of them. It was 16 pages per, so there should be 16 times 100, so 160 or something like that. So a lot of these objects all over the place. So we could go look for those pointers too. But yeah, easy kernel leaks. So one thing you might be saying now is, that's great. These two structures worked for this particular challenge, but how do you find structures that work for other challenges? Personally, I think most people just use lookup tables for these structures. There was a really good article, I can't find it anymore, that had a huge list of all the different structures that you can use, but if you just Google around, like there's only so many objects that actually get allocated that are useful. So I found this table here. Here's a bunch of different structures that you could create. We can see kmalloc 1k has both pipe buffer and TTY struct, so we were on the right track. Methods message wasn't usable in this case because we needed a leak, but methods message is one I'm familiar with that I used as part of Pwn College, and there's a lot of interesting things you can do with methods message because it allows an arbitrary size. And there's also if you can corrupt them, there's an X pointer, and you can do a lot of like fun arbitrary reads and writes. And then there's also this article that a lot of CTFers reference by ptr a famous pwner. And they list out all the objects and like how you can create them and some notes about them. The article is about 5 years old at this point, but still really good. You know, they talk about all the big ones like message and sec options and the cred and file. But usually you can just Google for the bin and someone has done a CTF write-up or something and you can find a good structure. And lastly, it turns out you didn't even have to do heap spraying if you didn't want to. Heap spraying was still the easier solution, but there's a fun write-up by Toma Dimitri, and we actually saw this person or this blog as part of the DNS rebinding attack. So I guess they're a master of web and Pwn, which is pretty fun. But they realized that there was a structure on the kernel that didn't respect ASLR, and so you could directly leak it. It wasn't the easiest leak because you need to find a kernel leak. You need to find a heap leak to calculate the offset to this kernel leak. So it's definitely easier to do the spraying, but still pretty fun. We can look at the structure. I think the address is somewhere. OXF here. So this address, kASLR should be enabled, but if we examine this address, specifically 0, we can see, and then you have to do +4, this is CPU start area, we can see these are kernel addresses. So at this known address, this has, you can tell there's no ASLR here, it has leaks to the kernel. And examine, I guess, entry text end. One thing that's difficult about this exploit, though, is you have to get to this address, you have to know where your checksum device is. And it is possible. You can create 2 checksum devices and then modify the name and like the position index of one of the checksum devices in tandem. And what you're going to do is just like read forward until you find both the name buffer and the checksum device, and then using those, if you know those two are linked together because you found both of them, you have the buffer to the name device, and you can calculate the difference between the checksum buffer and the name buffer, and then from there you know where you are in the heap, in the SLAB, and then from there you can calculate the offset to this, and then get the leak. So it is doable. It's just a little bit more work, but pretty cool. If you had a full out-of-bounds read and you're on this kernel version, this is definitely an easy way to bypass that ASLR or kASLR. Anyways, that's it. I'm glad I went back into the heap spraying. It's definitely, I should have done that from the start. It's way easier than just guessing and bit masking random addresses. But thanks again to Iris for hosting, and thanks again for all these amazing write-ups. I'm always excited to learn new things, and I'll see you at the next CTF. Cheers.